current walking on is common magnetic field.
Which word on the name?
the remaining ones start to rotate only due to the magnetic field. Investigate and explain the phenomenon. So in the review, we can see the experimental setups of the magnetic field. Well, there are two discs equipped with 16 magnets and 4 magnets. Between the two wheels is another wheel which is equipped with screws. So the screws will be magnetized by the magnet here, and it will affect the wheel here and make the wheel here turn, rotate. So this is our hypothesis. The phenomenon is related to the magnetic force, and the screws in the middle are magnetized, and so is the magnetic force magnet. So this is our experiment variables. For the first one, we are turning the wheel which has 4 magnets, and we are controlling the same distance, number of magnets, and the number of screws. So we are going to find out the ratio of turns. So in the experiment, we have magnetic gear stickers with marking iPhone for recording. And we have 3 steps. We're turning the wheel which has 4 magnets, we're recording the motion of the magnetic gear, and we're going to count the number of rotations on both sides in gears. So as a result, with a disc with 4 magnets rotates 4 times. The disc with 16 magnets only rotates once. So for another variable, we're going to turn the wheel which has 16 magnets, and we're going to control the same controller variables, and we're going to find out the ratio of turns. So in the experiment 2, we have the same instruments, and we got the same size. Besides, we can turn the wheel which has 60 magnets. So as a result, when the disc with 16 magnets has rotated once, the disc with 4 magnets only rotated 4 times. So we can find a ratio between the two discs. Between the disc with 16 magnets and the disc with 4 magnets is 1 to 4. So here comes our discussion. The angular speed of the wheel which has 16 magnets will affect whether the other wheel will follow rotation. So if the angular speed for 16 magnets, for the wheel which has 16 magnets is too fast, the other one will fail to follow rotation and rotate. But this is also the case for the disc which has 4 magnets. If the angular speed for 4 magnets is too fast, the other one, which has 60 magnets, will also fail to follow rotation. But if the angular speed for 16 magnets is low to some extent, the other wheel will follow rotation. And this is also the case for the wheel which has 4 magnets. So in the discussion 2, we rotate the disc with 4 magnets and the hand is removed. The rotation speed of the disc with 16 magnets will demonstrate the oscillation. So we don't have a video, just a picture. But while the wheel is turning, the markings will move back and forth, and which we call it oscillation. So we can see the comparative of these two discs in another paragraph. So in discussion 3, here comes the oscillation within 2 discs versus time. So when the disc which has when the angular speed which has 4 magnets is at the downhill, the angular speed of the wheel which has 60 magnets is at high hill. So at high hill, downhill, high hill, downhill. So we can say that there's some energy transfer between the 2 discs. So in discussion 4, rotating one side can make the other side start to rotate, or the magnetic gear has some certain distance. It is hard to be rotated if the distance is too short or too fast or too far. So if the distance between the 2 wheels is too far, the phenomenon of the magnetic phenomenon is too far to exhibit. But if the distance between the 2 wheels are too close, it may affect the other side of the rotation and makes it, maybe it will stick to the magnetized groups and it will affect the outcome of the experiment. So also the magnetic force needs to be within a specific range and it depends on the friction of the bearing, which says that the same magnet at distance but different bearings will lead to different results. At first, we are using plastic bearings as the axis of the experimental setups, but the friction coming from the plastic center is too high, so it will affect the rotation. So as our approval, we use plastic center as the bearing, which will reduce the friction of the bearing. So we got discussion 5. Magnetization and produce a tangent magnetic force and cause the other disk start to rotate in opposite direction. So it shows how the magnetic field works. Well, if you turn this side of the wheel clockwise, then the equation of these two forces will be a tangent magnetic force here, and it will make the wheel turn counterclockwise. So this is how it works. In discussion 6, when the angular speed of the disk with 4 magnets is less than about 9.8 radians per second, the disk with 16 magnets start to rotate. So I've mentioned that if the rotation speed of the disk with the magnets is too high, the other one will fail to follow the rotation. So we think that if the angular speed is not constant, it will follow the rotation. So we got the actual number of it, which is 9.8 radians per second. We use a tractor to conduct this analysis. So this is our conclusion. For our study, it has certain value of magnetic force to rotate the other side. It is also the same case as the distance. It has a certain distance of the two wheels to exhibit the magnetic phenomena. So, and the other one is the angular speed of the wheel will affect whether the other wheel will follow rotation. When we rotate the disk with 4 magnets and the hand is removed, the rotation speed of the disk with 16 magnets will demonstrate the oscillation. And the oscillation shows that the energy is transferred between them. And the reason why we just do an experiment for the disk with 4 magnets is because if we use the disk with 16 magnets, if the disk with 16 magnets is at a very high speed, you may think that if the speed is slow to some extent, the other wheel will follow the rotation. But our experimental outcome is that no matter how slow the disk with 16 magnets become, the other one will not move at all, which is opposite to the experimental outcome of this one. So this is our reference.
Okay. Let's get a component to report it.
They have to consider using different types of magnets because like different shapes or different orientations of magnets.
Meaning, so in the shape of magnet.
Yeah, like a different shape of magnet or a different rotation like
No, have it.
And did you try to calculate the magnetization of the spin? So since you use a torque, have you considered the acceleration or the angular acceleration?
What is it?
Like
Yes, we have tried between a 16 and 4-1.
I mean, like, other than like just looking for maybe like
Oh, the ratio remains the same if we use 16 and 4. But if you change the amount of the magnets, it will not show the same outcome.
and have you measured any magnetic?
No, we have don't have actual one.
Also, for your setup, doesn't a fidget spinner have like
Okay, time's up. Preparation of the opponent is ready. Okay, next up. Opponent takes the floor next to the floor knee.
obvious closing over set magnetic. The opponent, my ideal structure of an investigation is to first estimate the forces of the magnetic angles by looking at the different angles between them, and then to predict an angular speed. After that, we'll use the angular speed to compare that with the actual experiment, and angular speed to compare the experimental results. And then we can try alternative models, such as using the angular speed to get a differential equation to calculate the motion of spheres. But the opponent's the other person's structure of solving the problem is they have two wheels with magnets attached, and they track their rotation, and they also compare the oscillation. They discuss limiting conditions, including the distance between the wheels, the friction of bearings, and the initial angular speed. And they also explain why the through the magnetization of screws and also the magnetic force that moves the other thing. The proposal therefore, I compare keys of angular velocity to compare ratios. But the con have a graph or any sort of theoretical fit to show a relationship. First discussion will be how the shape of a sphere is different of a bigger sphere versus a field, and how we should measure the magnetic force and what it affects on motion, and also a magnetic force explanation. If the magnetic force causes a rotation, or like is the amount of ratio even matters or not. Tagline discussion. So why is it a real instead of a physics sphere? Because when you use a feel like the shape is a lot different.
You mean that the shape of the physics sphere is not the same as the wheel?
Yeah, because in a physics sphere, there's like holes in the middle of the physics sphere, so that would affect the whole shape, including the moment of inertia. And I think the moment of inertia is really important to calculate the force.
What do you mean that there is different shape?
Like, I show you. So a physics sphere is going to like have like this, where there's holes in here. So the variable here aren't really rotating like this way. And since like there's a hollow shape in this area, that would change the moment of inertia, which would therefore like change the square, and then which would change the like angular acceleration and would affect the motion calculus.
You mean that is not really a sphere? Yeah, I think that's wrong. I mean, that didn't actually give up the shape of the sphere. We focus on the place which is magnetic without the magnets.
And also, why didn't you measure the magnetic force? Like, I really need to measure the magnetic force between them because that could explain why, like, perhaps why that 9.8 speed was required to allow the other field to move. Or it might also show like why the field would rotate in a certain direction and not the other direction.
Yeah, we should have more statics like a force or something to make it convincing. But we lost our magnetic effect.
Do you have any explanation to why you specifically needed a 4-to-1 ratio?
But we were trying to dig into the experiment and find equation. And we found this is a special relationship between these three structures of these three structures. So do we, it is not important about the ratio?
I'm just saying that like the ratio could vary. And I was curious why you needed a 4-to-1 ratio. If, for example, if you had like two here and then a lot of if you look at it turning, maybe like perhaps like it would turn differently depending on like the interaction of the magnetic fields. So like maybe like around these areas there would be more interaction with the magnetic fields. Cause a different
Yeah, because the ratio of 4 to 1 you can use.
Oh,
Like 4, 16, and other one like 5 and 20. It is still 4 and 1. Yeah, so you can use the ratio to make other things like this.
And also, I think we should really measure the magnetic force. You could also change the way that the magnets oscillate. So, for example, like if you have like certain magnets that are like stronger, that would create a different like magnetic force, and that would be like uneven. So maybe like there would be like more turning around certain areas.
And we have something that we have discovered about the ratio. Because we can predict the screw motion.
How many is there like a certain ratio of the screw numbers?
Yeah. There is a 60 and a 41. So the screw make the screw is like this.
And do you have any explanation to why it is?
We only find the ratio, but we don't really know what it works. But if you don't follow the ratio, it works. It will not work. Like if you if you change the screw number to the other numbers like 10, 12, maybe they will move exactly different from this thing. Right? We have used other amount of screws, and the rotation of the two wheels is the same between them.
Have you ever considered a scenario where the wheels will rotate in the opposite direction instead? For example, if you flip the magnets over, that can cause like an opposite force
Oh,
attraction.
you mean to change the NS?
Yeah. I think that would matter because it's like it is like changing like if you change the NS, it might change the like direction of the field, which would like change the way that because we have like a diagram earlier about like the three arrows and the screw and how that like causes a motion.
Yeah.
And so that might change the direction of the arrows.
Yeah, it's good.
Also, I really recommend you use the physics winners because the problem with using this sort of circular shape is you can't create different forms of interactions. Like when you're using a physics, actual physics winner, then like, wait. Say I have like two physics winners next to each other, and that you have like attached magnets to the net. And if you have a different type of motion, or instead of like the two parallel wheels that you're explaining, you actually rotate them like this way, like in the same plane, which would cause a different motion.
Oh, I understand. And you will make a open translation too. Yeah. One will be slow and the other one will be fast. And for that, for a minute later, the other one will be slow and one will be fast. The distribution.
Yeah, because for this, this setup is more unique because because magnetic forces to like calculate the overall torque to get the motion. So I think like having like a non-uniform distribution would be good.
That convention, we don't consider these things in experiment.
Wait, what?
Because we actually don't know how to actually track the make a force number. So yeah, we should work on this.
If you want to try to force something, I actually recommend you like use a. So basically the formula is like force equals to like the gradient. So you can get the force equals to the gradient of the magnetic dipole multiplied by the magnet field. And this way you can actually like keep track of the force between two magnets. And then using that you can calculate a torque due to the force. So like for example, if you have like a force that's like pointing this way, then you can take the perpendicular component and then multiply that perpendicular component by the length of the length from the pivot to the magnetic dipole, and in that way you can actually calculate like the torque that the whole spinner experiences. So then using that you can predict the motion because through the torque you can get the angular velocity and I mean the angular acceleration, and then you can actually like predict the motion.
The change.
Yeah, so you can actually use like tracker, because tracker can give you the precise coordinates at every single moment, and then using that you can take the coordinates at every moment.
Okay, time's up. Opponents summarize the discussion for 1 minute.
So we discussed the J1 spinner and how the fidget spinner versus a wheel is different, and the moment of inertia would affect the force and the angular velocity, and it's also needed to fulfill the Paulus statement, as the Paulus statement clearly says that we need a fidget spinner instead. And also, if you use a fidget spinner, magnets to be in a non-uniform distribution because of the way that they can be able. So this way you can actually test the effect of the magnetic force to get a better analysis on motion. And if you measure a magnetic force, you can also better predict its force. And for magnetic force on motion, the opponent was only looking at the ratio of magnets and screws, but we believe that this phenomenon can be better explained by computing the magnetic dipole, as magnetic dipoles can more accurately explain how like different magnets will interact with each other and we can investigate the magnetic field.
Okay, thank you. Question of the reviewer before the opponent. 3 minutes.
The question for the opponent, since you have mentioned the shape of the gear in different parts, so how do you think the role, the shape of the gear playing with the from?
Shape of the gear.
Yeah.
So the shape of the gear, it changes the whole way your like mass is distributed beyond your gear. So that would change the moment of inertia. So that would just change like your whole angular.
The question for your fault. Will the mass of fidget spinner determine the result?
With what fidget spinner?
The mass of gear.
Oh, mass of the fidget spinner. We use the same source of the. We use the same source way.
How will the mass of the gear determine the result?
Mass of the gear.
Yes.
Well, the mass of the gear will obviously like if you use their setup, which is like pretty strong, like on parallel to the ground, then it would change affect the gravity if it isn't angled properly. So that would affect like the gravitational force and how that affects the ground.
Okay. Can you briefly explain how will the gear have oscillation?
If you have oscillation, if you feel like a magnet is like far from another magnet, and then as it rotates closer to another magnet,
sort of, it will reflect because it will change the output. It will in the effect for the first question you have mentioned. It will affect because of the graph.
Oh, okay, thank you. What do you think that will cause deviation?
What are deviation? What are you talking about? That will cause deviation.
Just for reporter, does the angular velocity which you rotate have boundary condition? It means that the passive field will not rotate.
You mean the other one?
Yes.
Yeah, I have mentioned that if we turn the other one, it will not show anything because the other one, no matter what angular state is in what angular state of the disk.
Thank you. In your hypothesis, the magnetic field is
Okay,
positive.
time's up. The duration of review is 2 minutes. Okay. Do you have to follow?
I'm a reviewer from Team South here. Today I'm going to review topic number 10, magnetic field. In the following statement, take several identical features and attach neodymium magnets to your ends. If you test them side by side on a plane and rotate one of them, the remaining one starts to rotate only due to a magnetic field. Investigate and explain the phenomenon. And we're going to focus on why does the remaining one start to rotate and the random parameter line will affect the phenomenon. A review of report. In this phenomenon part, his observation show that when you rotate one of the gears, the other gears will start to rotate due to the magnetic force. And his hypothesis say that in his experiment, he conducted by changing the torque ratio and different disks. And he has a lot of discussion. And the strong and weak point of the report, he has discussed the various conditions to compare the ratio. So in the weak point, we have unclear qualitative model, didn't have a theory, and unclear explanation of experiments, and analysis on experiments, and depth of variable. Review of those opponents. He has discussed about the shape of spinner, the moment of interchange of the gears, and noticed the lack of variable in the report. However, she didn't find out that it had found out the deviation in his theory. On his discussion, shape of spinner. Opponent think we can measure the force because the moment of inertia calculation is too complicated. Our question next. So we asked what the mass of each spinner determine the result. The opponent said not associated with the question, but I think it will affect the moment of inertia, which causes the force figure. Our question, oscillation. What will the gears have oscillation? The opponent said that the magnet will move until pushed by the other magnet. But I think it's a viscous damping and a repel force from the other magnet. And the missing point in this phenomenon, it didn't measure the rotating speed, which I think it will consider is a significant parameter in the phenomenon. And the theory part, it didn't have theory. In this parameters part, it didn't measure the angular velocity of passive gear at different thickness of gear and quantity of spinners, orientation of magnets, and the material of the plates. And in the experimental part, it didn't find out the boundary condition of different parameters. And it didn't take the deviation into consideration, which I think it will have a considerable error. Thank you.
Concluding remarks on the importance of 2 means.
These are our remarks about this experiment. So although we didn't measure the angular acceleration, it doesn't affect our result because our goal is finding out the relationship between two things. And our main point is the position of the magnet, not the shape of the magnet. It's the maximum magnetic field is on the side of the magnet. So put magnets on the position instead of using a big magnet. That doesn't affect the result of the So if there are many magnets, the mass of the magnets cannot be correct, and the result of the experiment will be affected. We have two future prospects. We could make more mathematical calculation between the magnetic force and magnetic field. And we can add more magnet in our future experiment, but the mass should be considered.
Okay. The jury, any questions?
I have a question to all three things. Can you give your own opinion on building the theoretical model for this experiment? Can you briefly give your comment on how to build a theoretical model for this experiment? Theoretical model. Theoretical model. Yeah, just give your own brief opinion on how to build a theoretical model for this experiment.
It's like what we showed.
Okay.
I think we can use calculation of the energy. We can when you rotate the gear, you have the kinetic energy, which is I times omega squared. And also have the potential energy is the real force, which is as vector mu dot vector magnetic field. And we can plus them together, and we can have a theoretical model.
Okay.
Then you can measure the magnetic force and also the magnetic field to notice how that can
reported use 16 and 4 magnetic, right? So suppose we increase in the 4 magnetic this side, for example 4 to 8, the velocity will increase or decrease in your all your opinion. Reduce. Okay.
I think it will increase because potential magnetic energy increase.
Increase.
So I think we'll also do increase.
No change?
I think it'll decrease because the magnetic force is sort of like a restoring force. So having like the magnets closer to each other will cause like that to decrease.
So in your opinion, decrease? Okay, decrease. So decrease, increase, decrease, increase. Right? Okay. Thank you.
Okay, so yeah, I would like to ask you of you, what kind of parameter do you think is most important to affect this experiment?
Maybe to friction.
Friction.
I think is the magnetic field intensity and
Magnetic field. Yeah.
I think like the direction of your magnetic dipole, I could like change the orientation.
Okay.
I have one question. Just have a brief comment to the report. Could you go to page 60? Give a brief comment. Because for any visual version, yeah, I suggest that
Excuse me, because the stage we cannot give any comment. If the score really works. Thank you. Please write down the score. Please show the score of reporter. The score of reporter is 4, 4, 4, 4, and 5. Please trace the score of opponent. The score of opponent is 5, 6, 5, 6, and 6. We show the score of reviewer. The score of reviewer is 5, 5, 5, 7, and 7. Okay. Thank you. Any comment? Please.
I just want to let them to specify the version what they did. Instead of using the arbitrary unit, because if your version angle is to have a specific unit, and when you quantify your result, then maybe sometimes you can find something.
Yeah, I know with that magnetic statics, so we should work on this.
The unit in the value axis is not specified, then you cannot compare.
Okay, thank you. Yeah.
I have one. I have a quick comment to the reporter. I think it would be great if you can use more scientific diagram or graph to support your experimental results instead of just using text. Yeah.
Okay. Yeah. Any further comment? Okay. Yeah. So then we'll finish this stage and we still delay. So please 5 minutes.